Welcome to lesson 1.5. Today we're going to look at significant figures, how to determine significant figures, and how to perform calculations and give answers in the correct number of significant figures. Just a few rules to begin with. Non-zero integers always count as significant figures. So non-zero integers would be things like 1, 2, 3, 4, and so on. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. All of those integers are non-zero integers or non-zero digits. Rule number 2 talks about zeros. There are actually 3 classes of zeros. There are leading zeros, captive zeros, and trailing zeros. And then there are exact numbers. Exact numbers really comes more into play when you're looking at doing calculations. And when you look at exact numbers, you don't use those when trying to figure out how to determine how many significant figures are in your final answer. So let's look back at the classes of zeros. If something is a leading zero, that means it precedes all non-zero digits. So they don't count as significant figures. So, for example, in this one, that one has 2 significant figures because this non-zero counts, and all 3 of those are what you call leading zeros, and leading zeros do not count. Now, captive zeros always count. Captive zeros are zeros that are stuck between non-zero digits. So here's a non-zero digit, here's a non-zero digit, and the 2 zeros are captive. So this has a total of 4 significant figures because that counts, and then both zeros count. Trailing zeros, a special rule for them, they count only if there's a decimal place. So if you look at this number, there's a non-zero digit. These zeros are trailing zeros because they come at the end of a number and there's no decimal place. So this one only has 1 sig fig, whereas this number, which is, as most students would think, is the same number, but the fact that it has that decimal place in there tells me that it has more significant figures. So in this one, those are trailing zeros, but there's a decimal place, so both of them count. So it's a total of 3 significant figures. What's nice about scientific notation is that anything in front of the x counts. So if you have a number like 2.00000 times 10 to the negative 2, then because it's written in scientific notation, everything in front of the x counts. So that has a total of 1, 2, 3, 4, 5, 6 significant figures. The advantages of using exponential notation, as I just mentioned, is that we can determine those significant figures very easily. And in science, sometimes we deal with very large numbers, sometimes we deal with very small numbers, and there are fewer digits needed to actually write a very large or very small number. An example here, this particular number is more conveniently expressed as 6.0 times 10 to the negative 5. So why did we put 6.0? All of these leading zeros didn't count. What kind of zero is that? That's a trailing zero. Is there a decimal? Yes. So in our exponential notation, we must include that 0. So that number has a total of 2 significant figures. So let's try these examples. Give the number of significant figures for each of the following results. A student's extraction procedure on tea yields 0.0105 grams of caffeine. So first, our non-zeros, 1 and 5. So there's 2. Now let's look at our zeros. What type of zeros are those? Those are leading zeros. Leading zeros never count. That one's a captive zero. Captive zeros always count. So that has 3 significant figures. Next one, same kind of thing here. There's our non-zeros. There's a total of 2. Leading zeros never count. Captive zeros always count. And what kind of zero is that? It's a trailing zero. Does it have a decimal? Yes, so that one counts. So 1, 2, 3, 4, 5 significant figures. And then this last one is easy because we just look at everything in front of the x. Don't worry about zero rules. That one has 4 significant figures. And that walks you through the explanation if you need it later. When you multiply or divide, the number of significant figures in the result is the same as the number in the least precise measurement used for the calculation. This has 3 sig figs. This has 2 sig figs. We go ahead and do that math on the calculator. We come up with this answer. Then we need to truncate our number so it has the same number of significant figures as the limiting term. So we would only have 2 sig figs in that particular example. What this does in scientific research is if you use significant figures properly, it shows anyone who reads the paper how certain your measuring devices were. Addition and subtraction, a little bit different rule. We need the same number of decimal places as the least precise. So that one has 2 decimals. This one has 1 decimal. This one has 3. Go ahead and do the math. And then we truncate so that we have the same number as the least precise. And so we would only have 1 decimal place in our answer. In terms of rounding, we're going to use regular rounding rules, although some science textbooks will have you do something special with 5, and I'll talk about that here in just a second. In a series of calculations, round off only after carrying the extra digits through to the final result. So that whole significant figure thing, if you need to do multiple calculations, you don't round until the end. You keep track of where you would round to, but you don't round until the end. And regular rounding rules, if the digit to be removed is less than 5, the preceding digit stays the same. So 1.33 becomes 1.3. If it's greater than 5, the preceding digit is increased by 1. So 1.36 becomes 1.4. Now, some science textbooks will say, what if you have 1.35? If you have to do multiple calculations and you're always rounding the 5 up, what that does is your end result is slightly elevated. But if you use the rule where if there's an odd number, you round up, even stays the same. So in this particular case, if we wanted to round to this place, then there's a 5 after it, so it's odd, we would round up. If it was 1.25, because that's even, it would stay 1.2. We won't use that particular rule in this course, but just know there are some science textbooks out there. So let's go ahead and carry out the mathematical operations in this particular. So go ahead and plug these in your calculator. If you need to, go ahead and pause the video. And let's go ahead and go to the next slide. This is another problem. Again, here are your values. Go ahead and pause the video if you need to. And so when you walk through A, you get this result. That result will have 3 significant figures because the term with the least precise has 3 significant figures. So here, that one has 3 significant figures, that one has 4, so our answer should only have 3. On this one, the result is 7 with no decimal point because the number with the least number of decimal places has none. So go back here. You calculated that out. And this has no decimal places. This has 1, so your answer should be rounded so you have no decimal places. And then the last one, we're going to go ahead and put that in the formula. Go ahead and do the calculations. And this is the number we end up with. And because we're doing a multiplication and division, what we're looking at is total number of sig figs. So this one has 4, this one has 2, that one has 5. So your answer should only have 2 significant figures. And so you would round off there and round that up to a 2. So what this shows is that these last few steps showed intermediate rounding. So you don't want to round too early. You want to go ahead and do all of your calculations. Notice that it is significantly different than this 0.082 that we got before. So just be mindful of that. Don't round until the end. So a few final questions here. Express 3, 1, 4, 0 in scientific notation. So 1 significant figure, 2 significant figures, 3 significant figures. That 0 is not significant. If we had a decimal here, we would move it that direction 3 times. So we would have 3.14. And what I have students do is I have them look at the number, and I say, is that a big number or a small number? Because we moved it 3 times. If it's a big number, that's a positive 3. If it was a small number, it'd be a negative 3. So the correct choice is 3.14 times 10 to the third. After performing calculations in the lab, this is what your calculator reads. If the number in the answers to have 5 significant figures, what result should you report? So these are not significant because they're leading. So significant, 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 significant. So we would report 0.02306. How many significant figures here? Non-zeros always count. Leading never count. Captive always count. Trailing if there's a decimal. So that one has 4 significant figures. Now look at these different beakers, and this is where significant figures really comes into play, is in lab when you take measurements. So if you look at this beaker, we know it's 26 for sure, and then we can guess one more decimal place. On this one, we know it's 20 for sure, and then we can guess one more decimal place. And on the last one, we know it's 26.4 for sure, and then we can guess one more decimal place. We're going to pour the water from these 3 beakers into one container. What is the volume in this container reported to the correct number of sig figs? So if we were to record this one, we would say 26, and let's just say 0.4. This one, we could only say it was 20, maybe 26. And then this one, we could say it's 26.42. And obviously, this last number is an uncertain digit. It's guessed. So if we add those together, this one has 1 decimal place, this one has 0 decimal places, and this one has 2. So our answer, if you're adding, can not have any decimal places. So the correct choice, or the only choice that would be reasonable on this one, is the 79 milliliters. So that brings us to the end of lesson 1.5. Next time we're going to look at dimensional analysis.